Riemann theorem strengthens this even more. Because as you could see, will ask us not that the modular differential is free, but just that the modular differential after you want torsion is free. And not only, it will not ask us that, you see this is really in terms of the Jacobian ideal, but the Jacobian ideal is they will bring R, but it only asks that the Jacobian ideal is principal. So much, much less. And so we'll get to that theorem, and why that theorem is so important? Because it leads us to prove, and that I'll prove, the purity of the branch locus, and the fact that to check that something is a ramified with certain assumption, it's enough to check in codimension 1. And if I have, at the end of the lecture, I'll talk about the conjectures. I don't know if I get to the different today, then I'll digest to the different only tomorrow. Okay? So, this is the length of the day. Okay? So there will be some skipping for the first time. So but I'll give you the idea at least. I cannot give you the idea of Riemann because that's hard to prove. So the first theorem, as I told you, is the first strengthening, and it says in our assumption, so you just have a local K algebra, as usual, K algebra. So let me actually write it like this. We already have a new field of essentially defined type. Over the blockade. And then it just says R is regular. Depend on if the modular differential is free. You see, it doesn't require anything about the rank. So that's really the point. The proof, we just have to prove this reaction, obviously, because we already know that it's regular, but the Jacobian criterion not only is free, but it's free of that rank. So we have to do the other direction, show that if it's free, then it will be regular. So we have to show that if it's free, it has rank T. So we can use the Jacobian criterion. So it's enough to show that the rank, so the rank, when this is 3, the rank is 3. Okay? So, and remember, this is 3, so this is R to the R, for certain R. You have to show that R is D. Okay? So you have to show that little r is D. Okay. So now, what we do? First of all, we take a minimal prime. So what I want to do, I want to go to the Artinian case. So we go to the Artinian case first. So this is a reduction to the Artinian case. And to do this reduction, we take P, a minimal prime of R, with maximal dimension. So the dimension, because I'm not asking R to be dimensional. So I have to ask like this prime as, I mean, if R is dimensional, it's obvious, everything my prime has that dimension, but I'm not asking that. So I want to get this prime. And now, what we know? We know that this guy is still free because the modular differential localizes. Okay? And we also know, remember what D is. D is this number. And the point is that this number localizes. That's a very important fact, that this number localizes. I mean, it usually localizes for if R is dimensional, but it localizes for every prime of maximal dimension. So let's see that, though it's very, very simple. You use the dimension formula. So the number locally would be this guy. The transcendent degree, look, is the dimension of RP, and then the transcendent degree of the residue field of RP over K. Now this is the dimension of this guy is 0, because remember this was a Riemann kind. And then this is the same as the transcendent degree of Rp, if you go check the formula over K, and this is the dimension of R modulo P. Now I use the dimension formula. So if you don't see why this is true, this is an easy fact. Computing the residual field of Rp. What is the residual field of Rp? Is R localized at P, P as P. Now this is exactly the transcendent degree of all Rp, because this is the same as the quotient field. Okay? Is this clear? So by the dimension formula now, apply the dimension formula to R modulo P. So you apply this dimension formula to R modulo P. Okay? And A is K. The dimension of this is 0 because it's a field, and then you have the transcendent degree of Rp over K minus the transcendent degree of K over K. That's exactly what we write here. So this is equal to this plus the transcendent degree of K over K. So we apply the dimension formula to K and Rp. Okay? And then this one, this thing is the dimension of R, because this was maximum dimension. And this is D. So the D localizes. Okay? And remember, if it's equidimensional, this tells you that D localizes more Riemann time. So no problem at all. Remember this fact because we'll use it without writing much about it. Okay, so now I can assume that R is at T. Okay, because I localize at P, that everything goes. So my guy now is an Artinian. Remember, I only have to prove that R is D, and the R is preserved, and the D is preserved. So you can assume that it's Artinian. Okay? Because I can go to Rp. So I went from R to Rp. That's what I did here. Okay? And now, okay, the dimension, remember, this we proved, this is the rank. The rank of this module, the dimension of this as a K vector space, okay, it's just a transcendent degree, remember? If it's algebraic, the thing is 0. This is just a transcendent degree. We proved it last time. But the transcendent degree, okay, of K, because the dimension of R is 0, is the dimension of R plus the transcendent degree of K, because this is 0, and this is D. So this tells you that this dimension is D. Okay? In this case, because it's an Artinian ring. So D in this case is actually the dimension of this thing. Okay? And now, you look at the conormal sequence. So I already used this. I want to use the conormal sequence with, like before, m over m squared. So you have m over m squared that goes with delta in K tensor omega R of K, which is isomorphic to KR. And this goes to m omega K of K, which is isomorphic to KD. Why is this? This is free, obviously. It's a vector space. And then I just say the dimension is D. So this guy is this. This is our assumption, that this is free of rank R. I need to show that R is D. So what do I need to show, guys? What do I need to show? That this is 0. That delta is 0. I have to show that this is the 0 map. Okay? Because matrix 2 will be isomorphic, and then R is D. So why is this the 0 map? All right? Suppose it's not. We'll get a contradiction. Okay? So what does delta do? Delta takes an element f and descends it, so an element here m over n squared, and descends it to 1, okay? That cancels the f. Okay, that's what it does. And the f is in f. And we assume that there is an f, there exists an f, for which this is different from 0, because delta is different from 0, with f in f. Okay? And now, this guy is free. So this has to be a minimal generator. Okay? So the f is part of a basis, because it's non-zero. Okay? As of omega rk, as the latter is free. Okay? So if it's part of a basis, its annihilator must be different from 0. Okay? So the annihilator of the f must be different from 0. Okay? However, then later will out. Okay? However, I'm claiming this is not possible. Okay? Because R is Artinian. And so the power of the maximal idea is 0. So let's see how I use this. Since R Artinian implies n to the s is 0 for some s. Because n is important. Okay?
You mean equals 0? The annihilator is
n to the s is equal to 0.
The annihilator df is.
Oh, 0, 0, you gotta be 0, yeah, sure. Instead I'm gonna find an element in the annihilator, sorry. Instead I'm gonna find an element in the annihilator, sure. Okay, so for some s. But actually, this implies that f of t is 0 for some t, but I take the minimal t, smaller possible t. So I assume ft minus 1 is different from 0, and ft is 0. What can you get from that actually? Do the derivative of f to the t. What do you go when you get the derivative of f to the t? The derivative of f to the t is exactly t ft minus 1 df. Now this guy is different from 0, and so it annihilates 0. And this thing has to be 0, because ft is 0. So t of t minus 1 is in the annihilator over I of df. And that's a contradiction. Okay? Yes?
So, couldn't it happen that df is part of a basis just after tensoring by k, but not as a...
No, because this is a free module. And so you have a basis.
Yeah.
So whatever, when you tensor with k, the elements that are a basis stays a basis.
Yeah, that's true.
And also the vice versa is true. Okay? So if you have a basis, you can lift it to a basis. So this is a basis element here, because this is a vector space is different from 0, and you can always lift it to a basis. I mean, it's easy to check.
Okay.
So that's not a problem. Okay, now that we have proven this, and we understand that freeness is enough, I can define the Jacobian ideal first. I mean, if you think about it, how do you find the minimal generator or module? Who asked me the question? What do you do with Banakayama's lemma?
Okay.
You tensor with K,
Yeah.
okay? That's easy. So now you know your answer,
Okay.
okay? Yeah. So, I want to this is really the definition of Jacobian ideal. And unfortunately, I cannot just be in this situation. I have to assume a little more the way I want to state it, okay? So let me, so so I assume that R is the localization, like you would always do, so this mod I times W inverse. Vectors just says that this is essentially a finite location. Okay? Nothing more. All right? So we are, same thing. I'm not assuming anything. This is just this. But now I want to assume something, and that's why I write this. I assume that the ideal I inside here, so every minimal prime of I is obviously an ideal in the polynomial ring, you know. Actually, I want to consider it an ideal in the localization. So let me do this. Let me just localize the top and then consider I an ideal in the localization. It's easier to do to ask. Okay? So I assume that the ideal I sits here, and I assume that every minimal prime of I has the same height. The height of I. Okay? Why do I do that? Because then I can set, that's the only reason, D equal n minus g, n is the number of variables, so it's really the codimension, okay? N minus g is the dimension of R, okay? And then the Jacobian ideal for R over K is simply the defitting ideal of omega KR. So now the fitting ideal does not depend on the presentation of the matrix. Does not. But you can take the Jacobian matrix and then you would have to take the n minus g minus. Remember? So this is the size minor you need. Okay? Because this is the defitting ideal. Clear to everybody? Because you are taking the derivative with respect to exponent sign, so that's the size of the matrix. Okay. Oh, sorry. Remember, this is different from the Kähler difference. Why? Because in the Kähler that we defined was the fitting zero. It was very different. That's the maximum minimum. This is larger. Okay? And we'll see the relation between the two very soon when we talk about difference. Okay, so this is the Jacobian idea. And now, I want to just remark two things, which I don't prove, but the proof is not difficult.
Quick question.
Sorry, yes.
The K in your subscript of omega, is that all here with
No, I didn't understand. This is small k.
Oh, great.
Small k. Yes, yes, yes. And this is small k too.
Yeah, that one I got.
Yeah. This is also small k. I don't, big K doesn't appear here.
Great.
I didn't need it, but I needed, even here I didn't need it, so like I can do this. I now need it in the definition of the percentage. Yes?
In the definition of the Jacobian ideal, in the parentheses, it's R over little k, right?
Yes, everything is little k. So this is little k. This is little k. There is no big K. Okay. So let's see the remark. The first remark says that D, what we saw before, and you can prove it very similarly, that D localizes. So for every P in spec R, so remember this fact, it's very important, the dimension of RP plus the transcendent degree of KP is always D. And this is because in this situation, because we assume this thing about the minimal prime, okay? All right? So we're using this. Very good. So this is always D. So D localizes, like before we edited the minimal prime. Okay? And so D does not depend, and it coincides with this one when the ring is local. Okay? And then the second remark is that the Jacobian method is the Jacobian localizes. And this is obvious because the omega localizes, and fitting localizes, so everything localizes. Okay, so now I can define the singular locus. I mean, that I suppose you will see many times. The singular locus is the Q by car such that Rp is singular, so is non-regular. Okay? And now it's clear that the regularity of R is determined by the modular differential. Like before, being ramified is determined by the modular differential. So now we know the locus, how to write the locus. So the corollary we actually don't have to do is that the singular locus of R is exactly V of the Jacobian ideal. Okay? Because this tells you when it's free of that rank. Because remember, the fitting ideal tells you exactly the locus where this guy needs at least D plus 1 generator. Okay? So this is exactly. So who determines the singular locus? So this is the very important fact that the singular locus is determined by the Jacobian ideal. Now, again, a little bit about D, actually about the rank of omega. We want to understand when omega is a rank. Obviously, phi is regular, omega is free as a rank. But not every module is a rank. So we need to understand when the modular differential has a rank. And this is very important, and this is this characterization, which for you come for free with whatever you did so far. And the proof is written here, I just sketched it in words, just telling you, but it's very easy now. So it says this, same assumption as here, I'm not going to write this. Same assumption, I just do this same assumption. So I'm always in this assumption. Okay? And omega as a rank, call it corollary if you want, and is a characterization of rank. As a rank, if and only if R is reduced and equidimensional. Again, so you can characterize the fact that R is reduced in equidimension in terms of the modular differential. Look how many things the modular differential tells you about your ring. Whether it's ramified, whether it's singular, whether it's reduced and equidimensional, you can read them all off omega. Okay? And the rank is necessarily D. So you cannot have other rank. If he has a rank, the rank is D. Always. D. Okay? Which is our D. The D that is here. Okay? Always the same. The dimension of R plus is different than degree. Clear? Okay, this is important. How do I prove this? It's a if and only if. Okay, so R is reduced, is a local condition. If and only if is reduced at every associated prime. Okay? And if it's a two-dimensional, these are just minimal prime. So you have to just check reducedness and equidimensionality at the minimal prime. Okay? And now, So now you are done because at the minimal prime, okay, this is a saying that is reduced means that is free. So this condition is equivalent to the fact that R localized at P is free for every minimal prime and R. But if it's free, sorry, it's regular, what did I say? Sorry. So this condition is equivalent to say RP is regular for every P in the minimal prime. So it's really equivalent. Because if it wasn't equivalent, if it's not equivalential, we cannot just check the minimal prime. Okay? So it's equivalent to this. But now use this. This localizes. The modular differential localizes. So this is regular. If I don't be locally, this is free. But to check that, what does it mean to be locally free? It means to have a rank. That's exactly what it means to be rank. To have a rank means that when you localize at the minimal prime is free. Okay? So this guy has a rank. And then you just have to show that delocalizes, which is already what we said before. And I told you, remember it was part of the proof I did before when I told you if the minimal prime are the same, they remain the same. But this is a minimal prime of the same dimension. So you're done. Okay? So that's a proof. But I've written all in detail. So the sketch is this one. Now let me do an example and then go to the real difficult theorem, which I don't prove, which is Lippmann theorem. So, I'll do more time, I have an hour. Okay? So now, I'm going to so this fact I need, and it will stay in the board. The fact that they are in the rank, this one stays in the board. And remember, the singular locus is just B of the equivalent. Okay, so these are all the facts to keep in the board. And then we work out the rest. Now, the first example, actually the only example I'm going to do now, but you have lots of problems, at least one or two problems about this, to find a singular locus. So you look at this guy, this is a very easy case, x squared minus yz. And now, to find a singular locus, you have to find, obviously, the Jacobian matrix, because this, you know, is a fitting idea. So I need just the Jacobian. So I need to know how this is presented. So the modular differential, this is R, of R over C is presented. I have to just do the derivative. This is just a row. So I have to do the derivative with respect to x, to y, and the z. So 2x minus y and minus z. Okay, these are the three partial derivatives. And now, so in particular, what is the fitting idea? The fitting idea, if you look at D, is just the ideal of entries. 1 minus g, and you get the ideal of entries of this matrix. And so the fitting D, which is Jacobian of R over C, is of omega, is exactly the ideal generated by x, y, z. Okay? So this tells us what? That except at this point, this ring is right. So it tells us it's moved. Because it's regular with bunch of spectrum. Okay? Now I want to go to, so in the notes there will be actually two theorems that I cannot prove because they are needed for Lippmann proof. Actually one of them is really, really interesting. It tells you what happens when you have a derivation from R to R, a derivation but send x to 1. Okay? Then this implies that x is the non-zero divisor and not only that if the ring is exactly complete, X splits off. And this is a very beautiful trick. So even if you don't go through Lippmann proof, at least read this, because this is very beautiful and very useful. So, but Lippmann theorem, that's what we need for the purity of branch locus. This says, again, same assumption as here, and save time on typing the assumption. And it just says that the following are a theorem. As I said, think of it as a strengthening of the Jacobian criterion. So we go through all three and weaken all three, except for the first one. R is regular if and only if the Jacobian idea, so the modular differential over its torsion is free. Okay, so after you want torsion, and then, which by the way shows that, you know, notice that it says that this is free after without torsion, but when you apply that meant was free. Okay? So there was no torsion. And then R is reduced and two-dimensional, what I need for the rank. And is what I need to have the D that stays the same. Okay? And the Jacobian is principal. So this is really a relaxation of this that says this one, if you write it in terms of the Jacobian ideal, this really tells you that the Jacobian ideal is up. So you can rewrite this now if you define the Jacobian ideal. Simply say that the Jacobian is all R. You know, it's not proper. Yes?
I'm a little bit confused about the two different capital D's that have been defined.
I mean, you can check that this guy is the same as this.
They're the same, okay.
Yeah, that's what I said, that they are the same. When I said the remark, that they're actually the same. Just check it, they are the same. That's why I need this condition here. Yeah. I'm not doing all details, but yes, that's it. Okay, so I'm not proving this theorem, but I will use this theorem. Okay, the theorem I'm going to prove now, slowly, is the purity of the branch locus. Let me see what I want to erase. Maybe I erase everything except this and Lippmann theorem. I'll free these two boards. Okay. Anyway, I need more assumption now than what I put up there. So, I'm cleaning this. And I even rewrite this in terms of the Jacobian book. You know, the fitting B is the Jacobian. So I don't need it like this anyway, because I need it. Okay. So, purity of the branch locus. I want this page and this page. Okay. Yes.
In our example, should that ring be localized?
Yeah, you can localize it, yes, but I think about the graded situation.
Okay.
That's what I'm thinking, about the graded situation.
But
This is homogeneous. And this, I will go to the graded situation, is usually actually easier.
Sure. But,
Okay? But you can localize if you want.
Great.
If you think about homogeneous, that tells you exactly that is moved, about the variety that tells that is moved. And if you localize it, then at the maximal idea, this just tells you the local ring is regular, that is about just right.
Okay.
Fine.
It's just that then we wouldn't have the Jacobian being principles.
Yeah, but everything localizes, so
Yeah.
you can do it in the graded situation. But you're right, I already said it in the local case, so I should localize. Everything I did was local, so. Okay? So you have a field of characteristics 0 as usual. I'm not going to write it, remember we're only in characteristics 0 here. Everything is defined. So here what I assume is that this guy are domains. So this is something I have not assumed before. Okay? So obviously you have equidimensionality and everything else, okay? So they are domains. And essentially a finite type over K. Let me write it like this. And then I assume also, and that's another big assumption, that the extension of the quotient field, because their domain is a quotient field, the field of fraction, is algebraic. So two big assumptions, domain and these are algebraic. Okay? When I assume that A is regular and I is S2. Okay? And then the conclusion after all these assumptions, so A is regular, I is 2, the assumptions are all underlined. Then the ramification locus either is the empty set or is pure of codimension 1. This means that to check that something is a ramified, you only have to check the dimension. Okay? So let's prove it. And as I said, if I have the tail missing in the border, all the, I make sure that all the tails are with the frames written out. Okay, so you can assume that it's not empty, otherwise it's trivial. So let's assume that it's not empty. Okay? And now, sorry? S2. Set condition S2. You know, which just means that the depth of the ring locally, okay, is always at least 2 for every prime that, you know, so it's come equally if the prime has dimension locally, if the prime has height less than or equal than 2, if the dimension of a p is less than or equal than 2. And for prime of dimension higher than 2, you just know that as depth at least 2. Okay? This is our condition as 2. Okay, so proof. As I said, we can assume this is an empty, otherwise it's trivial. Nothing to prove. Okay? And R over A was not A. Okay? And now, remember that we know already that this is a closed subset. Okay? And remember, we know very well that it is defined by the support of omega. Okay? So this is very important. That this guy is really just the support of omega. Because this is a ramified if and only if omega is 0. Okay? So now we localize at the minimal prime of this. Okay? So localizing at the minimal prime, because we have to check only that is pure codimension 1. Okay? So the minimal prime of the ramification locus, okay, we may assume that this ring is local and the ramification locus is the maximal area. Okay? And well, you could ask, why can I do that? And the modular differential localizes. That's all. Okay? And remember that the ramification locus is defined by this guy. So I can do it. Can always localize. And now what do you have to show? You just have to show that the dimension of your range is 1. Because you have to show that this prime as I want. So you just have to show that. Suppose it's not true. We get a contradiction. Okay? So we have to suppose the dimension that is true and then we get a contradiction. So it's clear that this R cannot be, the dimension, okay, of R cannot be 0. So it has to be different from 0, cannot be 0, because if the dimension was 0, remember, these guys are domain, then there would be fields, okay? And then you would have, and the extension is algebra, okay? So the modular differential would be 0, and then the ramification locus would be empty. But we assume the ramification locus is not empty. Okay, so our assumption tells us that this dimension cannot be 0, all right? So we cannot, so the contradiction just can come here. Clear for everybody? Okay, so we can assume the dimension is at least 2. And remember, D is our dimension of R plus, so I can actually write it as the transcendent degree, in this case, of A over K, which is the transcendent degree of K over R. Okay? Remember that this sum was also the transcendent degree of R, the quotient field, over K. They are algebraic. Okay, so it's the same transcendent degree. This is very important. This D was this, but we had also proved that D was the transcendent degree, we proved it the first time, of the quotient of R over K. Remember? But in this case, the quotient of R and the quotient of A are algebraic, so it's the same transcendent degree. Okay? Alright, guys. So we are in a good condition. And now you have to look at the cotangent sequence. So not this one. I didn't write it down, but you should remember it. Hopefully you remember it. Okay? You look at the cotangent sequence, and what we know that this guy is regular. Remember? So what does already the Jacobian criterion tell us? That is free. Okay? So we already know that this fellow is just some copy of A. How many copy of A? The D of A. But you can show, it's easy, just a second is in the notes, that D of A is D of I. They are the same D. Okay? So because it's actually here, they are the same key. So this is A to the D. Okay? This is telling you that the D are the same. So this is just A to the D. Okay? And now, so in particular, this thing is R to the D. Right? Okay. Now what we do, let's call this thing, we consider the same sequence and we go modulo per alpha. So we want to use Lippmann. And this guy you have to call C now because this is going to be somebody different, okay? But you still have an ecmorphic image because there's one modular portion, an ecmorphic image here, and here another man, which I call C. And this is R, the same guy. Okay? And now the first thing we observe is that this one, so this first observation, this thing is injected. Okay? Which tells me that this is injected. Why is this injected? Because the kernel of this man is 0. And why is the kernel 0? Because the kernel has to be a torsion. But this guy is torsion free. Okay? So this tells me the torsion is 0. Okay? Another way to see it, if you want, I mean, why is all torsion? Because remember that this guy, by assumption, has dimension 0. Because we are assuming that this is the ramification locus, the maximal ideal. So the dimension of this guy is 0. So the dimension of this guy is 0. Okay? So this tells me that these two are the same rank, because if this has a rank, the rank is T, these two are the same rank, so the kernel has to be, torsion, because we are having two modules of the same rank. But the kernel is inside here, this is 3 is torsion free, so the kernel is 0. Okay? So first argue using the fact that the dimension of this is 0, the dimension of this has to be 0 or less than equal 0. Okay, which tells you that these two are the same rank, but the rank, and when you compare rank, the rank of this is D, the rank of this is D by this corner that I did not erase, so we have the same rank, so the kernel is all torsion, and then the kernel has to be 0, because the kernel is torsion free. Okay, so we have injectivity, and now that we have injectivity, we just play with that, okay? That's what our assumption of S2 comes out. Regularity we already used. We used it fundamentally here. Okay? Now we're going to use the S2 condition. So the S2 condition tells us about the depth of these guys. Because this is RD. So it tells us since the dimension of the ring is at least 2 by assumption, that's a bad assumption, this guy has depth at least 2. Okay? But this guy has depth at least 1. Okay? Because this is torsion free. And so the depth of C is bigger than equal than 1. Okay? Now that tells you that C is 0. Because at dimension 0, how can I have depth? It's impossible. So this goes away. All right? Okay. And now, so this tells us that these two are isomorphic. So this guy is RD. Okay? Sorry.
Vector C must be this one.
Because we use the depth lemma. The depth of V is remote order. So it's positive depth. The depth of T is at least 2. This is an exact sequence. The depth of this is at least 1. But this has dimension less than equal than 0, so it has to be 0. So this is RT. But when you use Lippmann criterion, if this is free, then this R is regular. Okay? Alright. So, and now we are done, because this, again, from here, you would get that, where is it? So this guy would have positive depth. So this guy must be 0, 2. And that's impossible. Okay? So this tells you immediately that this is 0, but we assume it's not 0. So that's a contradiction. So you get the contradiction right away. And now this is the end of the purity of the branch locus. And I said, if the detail are not enough, because it's all written like this in the board, please just look at here. There is everything. And there is a proof of Lippmann. Okay. Now I would like to, before going on, now I want to talk about the famous conjecture. And when we go to the difference. So I think I have time to briefly talk about the conjectures and then start the difference. So tomorrow I can even talk more about the difference. And tomorrow I'll tell you what I want to show about the difference. Maybe today I tell you what I want to show about the difference and then we start. So let me erase this because I'm done in the beauty branch locus. So the reason I point out this conjecture is the fact that I would like to tell you to try to work on this stuff, because there are still a lot of open problems. And even if you're not convinced, because these conjectures are very hard, I'll tell you why it's good to know about the modular differential. I have used it in so many unrelated papers. I mean, just recently I wrote a paper with Sid Ruiz and Ulrich, and we use very much the diagonal ideal and the stuff that comes in the proof of the difference, in a completely different related thing. Okay? The lecture, series of lecture I wanted to give here were actually about, not this, but about vector fields and curve left divided by vector fields. And there is really all a study about the modular differential and about the modular derivation. And the big question there is, what are the Betti numbers? Even in cases in which R is a very easy ring, the ideal I, the defining ideal I is given by Hilbert-Birch matrix, you still ask, what is, the Betti number? And these are very important questions that are related to many other conjectures about curves. Say if you're interested in geometry, okay? So there is a lot of stuff there and a lot of good problems for young kids to go to. But let me tell you the conjectures. These are hard. So you have to, people have tried, okay? So I'm assuming, again, the same assumption, which now obviously I took out and I should add it. So they are R is R and K, okay, and is a local K algebra. Essentially find it out. Essentially find it out over K. I'm not always shocked and shocked at the same time. Okay? And then I assume that is reduced. All right. And obviously, remember, D is the usual number, 0, so you don't have to write. D is 0. So this is the situation. The first conjecture I want to point out, there are 3 conjectures. The first one is called Berger. This was Ulrich advisor, so it's not surprising that I learned all this from Ulrich because his thesis was about this conjecture. He didn't solve it, but he did solve some cases of it. So in this case, we assume that D is 1. And obviously, you can see immediately that it's actually reduced to the case of dimensionality 1, otherwise it's trivial. And we can see that omega is torsion free, that's what the conjectures say, if and only if R is regular. So it's very much connected to what we did before. Okay? But in particular, torsion free implies freeness. This conjecture is really about points in a curve. Okay? Think about it that way. And it tells you a lot about the singularity of these points. So, it has been proven in the case in which the ring is regular, by shear fudge, and that has been proven by Berger for, I think, almost complete intersection, and by Ulrich for small deviation, I think up to deviation 3. After that, it's completely open. Okay? And so if you don't know what deviation means, it's the difference of V. R is defined as a quotient by an ideal I. Is the difference between the height of the ideal and the number of generators. So the almost complete intersection means that this difference is just 1. Remember, the number of generators of an ideal is always bigger than equal when it's up. That's principalized, cool here. And if the difference is just 1, if they are equal, it's a complete intersection. If the difference is just 1, it's called an almost complete intersection. Otherwise, that difference is called deviation. Okay? So for ideal, with small number of generators, imagine the idea, respect to the height, it's been solved, but in general it's open. The next conjecture, which is false in positive characteristic, it's almost known. Almost completely known, and it's called the Zariski-Lippmann conjecture. is the one I was talking to you on the first day of class. And this says, you are always in characteristics. This actually is characteristic free. The next one is characteristic zero. So this is interesting in a positive characteristic. This is the only characteristic zero. Very important, because it's false in positive characteristic. And it says the modulo derivation is free if and only if R is regular. Okay? That's what it says. And why is almost known? It's almost known because, I mean, the greater case is Webster. And if it's not, in the general case is due to Flanner. Flanner, though, assume, okay, that the links are true, regular codimension true. If you don't know that, that is okay. So you have to solve that case. So it's reduced to prove it when you have common dimension, stuff like that. So, but again, this is almost done. So we know that it's true. I mean, but though, it would be a big thing to prove it, to completely prove it. The next conjecture is that is due to my advisor, Vasconcelos, which unfortunately passed away. And this one is about the projected dimension of the modular differential. And it essentially says that the modular differential has only three possibilities. Either it's free, which means the ring is regular, or as projecting dimension infinite, so it doesn't have project, or it has projected dimension 1. So if the projected dimension is finite, it can only be free or projected dimension 1. That's what the conjecture says. We still don't have counterexample. This is completely open. The only result towards it is a recent result of Briggs, with Benjamin Briggs. That's how it is in Utah. There's still a postdoc in Utah, no? No. What is his position?
MSRI.
MSRI. So he's an MSRI. Okay? And I tell you what he did. I mean, I don't tell you what he did. Maybe you were in the national seminar, you heard what he did. But I can tell you why they imply this in some cases. So that says projected dimension of omega of R over K is fine over R, is finite when R is a complete intersection. And this is the same as, say, the projected dimension of R of omega is less than equal to 1. Either it's free, if it's regular, because complete intersection can be regular, and if this is really a complete intersection which is not regular, that means that the projected dimension is less than equal to 1. Okay? You use the polynomial sequence for that. Okay? Practically you have equality, and this I over S squared is 3, and so the projected dimension is just 1. So, because if it's a complete intersection, that's an important thing. I over S squared is 3. It's very, very easy to show. Okay? Remember, I defines R. Sugar. But you have to, I don't wanna make more mess. So the reason is really that this guy is 3 and then this is actually short as that sequence, and that's a projected dimension. It gives you the projected dimension 1. Now, why Briggs proved it in a certain sense? There is another conjecture of Vasconcelos. And that conjecture only talks about the conormal module, I over S squared. And that conjecture says practically the same thing about the conormal module. It's practically the same, but it says that the projected dimension of I over S squared is finite if and only if R is a complete intersection, which means I over S squared is 3. Okay? I define R, so be careful to that. It's not the same R that you have in the first one. That's why I don't want, it's the same as T in that one. So, you see, R is this guy in this one. That's why I thought it's complicated. This should be called R of high. R is this one, and this is the polynomial ring, and that's the idea. That's why I said that you may be confused. All right? So be careful to that. Here I should maybe say that, because I defined R, I should say, I call it S, I don't know, C or T, maybe T. When you're happy because I called it T before. Okay? And it's easier. And T is this guy. And you see, if this is 3, the projected dimension is 1. Okay? So the thing is very similar. It says projected dimension of the normal module is finite, implies that R is a Cubic intersection, which means it's actually free. So that guy can only be free if he has projected dimension 5. That's what he says. And he proves it. He proved it almost, I think, quite in generality. I mean, there are some assumptions, but it's almost almost consensus. Not all, but almost. I mean, it's a big stuff. And now, this though is not proved because, why is not proved? Because it's proved if the symbolic power is the power, okay? Because otherwise you cannot do the connection, okay? But if the symbolic power is the power, then it will become the simple conjecture. That's your last, you know, in the last set there is a problem. You'll understand better when you do it. Okay, I think I took a lot of time to describe the conjecture, just to entice you to work on these things. Look how much I do to entice you to work on these things. I care very much that you work on this. So now I want to introduce the difference. So this is about the difference, which, you know, this was actually another series of lectures. I thought I would give just the difference, and obviously it didn't become that. Because I wanted to talk about recent work I've done with Ulrich, computing difference, but it's clearly not possible. So let me just tell you about what the difference are. So this first is the complementary module and the free difference. Okay, so before I go on, let me tell you where I want to get to. So we already defined one guy, which was the Taylor difference. This was very easy, was defined by the usual setting. And if you remember, what was we call it D of K, to be different K, or R over A, okay? And this guy was simply, you remember, the hitting zero, because it was the guy that determined the ramification result of omega R over A. Remember? So maximal minor of the Jacobian matrix. Very easy to compute, very easy to understand, define the ramification loci. The next difference we want to introduce is called the measure difference. From the name, it should be clear that the person that introduced it was Abinator. However, the paper where this is introduced is maybe 50 years after her death, because they found the paper in her things and all the theory in her things, and then they publish it, okay? And it's actually very, very beautiful stuff. And then the guy that was defined first, much earlier than none of this, because it's defined from number theory, but is harder to define, is the Derivations difference. This guy, as I said, his roots are in number theory, and because of that, you need trace to define it, and so it's really defined in a much more, restrict setting, respect to these two. You need a lot of assumption about your ring to define it. Here you just need an essentially finite algebra. Actually, here you just need an algebra, an A algebra. So here you need more because you want the modular differential to be finitely presented. But that's all, okay? But here you need much more. And we define this via another guide, which is called the complementary module. And this guy is simply the inverse, okay, of this. And this is a very important guy because it's really a canonical module of your ring. But it's not a canonical module. Remember that the canonical module are isomorphism, but there is not a canonical isomorphism. However, this is the canonical module because it's the most important and you can prove that it's the one of, anyway, I come to it. So really this is isomorphic to a copy of the canonical module, but the most important one. Okay? And then what we want to do? So first of all, we want to prove that there is a relation among these guys. So this is easy to compute. This has the best property, it's usually mixed. And this is in between, okay? They all three, and we prove some of it, define the ramification locus. All three, okay? But with a very different scheme structure. And what we prove, the main theorem, is that dk is contained in d n in the order is contained in the delegate. So we prove the containment, okay? And obviously the interesting thing is when are they equal? And not only this, we prove that these three guys are contained in the conductor of R. Okay? So they are contained in R column R bar. R bar is the integral closure of R. Okay? And furthermore, we will show an important connection with the Jacobian ideal and with the circle of the array. Okay? And these are also very important. So we show a connection with the Jacobian ideal, which is very important for the Source-Coda kind of theorem, and with the circle of the ideal. So what we want to also do more, we want to characterize when equality happens. So this is actually a very important question in general, still open, okay? So we know only sufficient condition. So if the ring is a complete intersection, you have equality here. If the ring is Come-Equally, you have equality here. And that's what we'll try to prove, okay? The proof are in the notes, but if I get to it, I'll prove it. R Come-Equally equality here, R complete intersection equality here. Okay? Obviously, it could be that they're equal more often. In fact, that's what we prove in the paper with Ulrich. We prove when equality happens, for example, if you have determinantal ideas. And we actually describe them very explicitly, much more explicitly than this. Okay? So, very easy to compute. And very nice, and they give a lot of formula on complementary module, canonical module, that is generalization of work of Ulrich and Eisenberg. Okay. So, now, I'm going to start, and I'm going to define the nether different, okay? And I'm going to, so the other thing was relation in that something in Jacobian. Okay? So first of all, I'm going to talk about the nether different and relate these two. The reason I do this first is because here I need less assumption. I don't need all the assumption that I need when I introduce this two. So I still want to work just with essentially a finite time. So I do this part of the story. At least I started today. Okay? So the dedicating and the later. So the later, sorry, the later and the later. So I just have to define now the later different. So to define the later different, you have to go back to the third definition of the modular differential. Remember, the third definition used the enveloping algebra. Okay? So we had the diagonal idea was the kernel of the multiplication map from the enveloping algebra to R. Okay? And we had proven that the modular differential of R over A is an R algebra, remember? This guy is R tensor A over R. Okay? The modular differential is simply isomorphic to D over D squared. okay, which you can also write as R tensor B, okay, over RE. Clear? So this is what we knew already. And now it's going to be very easy to define the, now if you remember this, it's going to be very easy to define another difference, because another difference simply this. So we consider the annihilator of this guy, okay, so let me see where I have my things. Oh, yeah, dot T. Okay, and then this obviously is an area idea. So it sits here. It's the annihilator of the diagonal idea. And then we push it with mu. If you want this R, you can also write it like this. This is the same thing. It just means, yeah, you're standing, I mean, yeah, you push it to the map. Okay? And this is the method difference. Okay. Now, so it's just the image of the annihilator of the diagonal idea. So why the containment of this? So if you want, the proposition is as following, and I said I move this first because the condition of rest, I only have essentially finite type, okay? So I only have R is essentially a finite type, okay, over A. And A is Euclidean, nothing else. There is nothing at K, nothing. That's all. R is essentially a finite type over A is an algebra, and A is an Euclidean. Great. Then the later difference contains the pair difference, and they are both contained in the annihilator of omega. In particular, they are both contained in the radical, which means they define the branch order. Okay? It's much harder to prove it for the derivative, so that's why I don't prove it, but for this is easy. Okay. So the proof of this statement. So this actually is not hard, okay? It only requires to know a little bit about fitting ideas. That's all. So first of all, you have to observe, so here we write the modular differential like this. Remember, okay? And notice that R is essentially for a type over A, and A is Euclidean. Okay? So R tensor R is also Euclidean, because it's essentially a finite type as well. So this ring is Euclidean. Okay? So D is finitely presented. Okay? Why do I care? Because if it's finally presented, I can relate the annihilator to the fitting idea. Okay? Because he has a presentation matrix. And then the fitting 0 of D, okay, remember this is the fitting as an array module, is contained always in the annihilator. This is an ideal nullity, so you have to do all of the fitting nullity. And this improved this relation. And this is actually what does everything. Because, remember, this is a fitting idea, so that's good to relate it to fitting ideas. So what does this gives us? let's erase the first board now, because we don't need it. So, we don't even need the D here. The big D, we don't need anything anymore, so I can erase this board. And at least I can prove it's continuous. So first of all, maybe more than the quality that we started. Okay, so what do we have? We have that the scalar on R of A, okay, is the fitting zero of the modular differential. Okay? Don't get confused, this K is not a field, it's a scalar. Be careful always. And this is the fitting of D over D squared. Okay? Over R. I always put the rings to be sure that you know where we are. Because there are two rings flying around. Now this is the same as the fitting zero over R. D over D squared, as I told you, is this. Okay? And this is the same because fitting ideal commutes with the base change. So it's the same as looking at the fitting zero of RE of D and then extending it to R. And now we finally have our relation because now here we have exactly this fitting zero. So this tells us that this one is containing that once I push it to R. Okay? So let's put it all together. You get dk of RA is equal actually R of fitting zero RE of D, okay, which is obviously contained in R of the annihilator because of what we wrote there in RE of D, okay? And this is the same, as I told you before, as the normal difference. And the proof is finished. Okay? So we have the proof of the containment. It was very easy. I didn't finish everything because I only proved this. I have to show you that they have they define that up to radical they are the same, that they are containing the radical, okay. So to show that, okay, so now you have the containment. To show that they are in the radical, how do you see it? Let's go back. Remember that dk is contained there, so we look at this annihilator again, this time, because that is the end. I have to show that that's somewhere. So this is obviously contained in the annihilator over R of R tensor RE of D. And this is easy to check. Okay? And this is the annihilator of omega. Over R. So that is on this containment. And now you have to show the last one, but that's a usual thing. It's true that the fitting is also in the homework. The fitting is contained in the annihilator, but the annihilator is contained in the radical of the fitting. And then finish. Because this is contained in the radical of the fitting angle, which is the radical of the killer difference. So this does the end of this, and okay, I have 7 minutes, but yesterday I told 6. So it's up to you. I can start proving the quality, but I think I'll let you go. And next time, I at least prove, better prove for sure, the quality when we have a complete intersection, okay? And then I introduce the Kähler and the Dedekind, and I give you the idea. First of all, I show you the relation with the Jacobian, the fact that the Jacobian is contained in the conductor, because that's very important in classical. And that comes immediately once I introduce this thing, given the inclusion by gravity. And then I try to give you the tools to read the proof of the inclusion and the quality. I may not prove it, but I give you the tools to prove it. Okay? The idea behind it. And then if I have time, I talk about the SOPL, because that's a beautiful story. Maybe I try to not do some proof and prove the SOPL issue. Okay, guys, tomorrow we finish.